To measure the accuracy of our forecast, we use something called mean squared forecast error. And this mean squared forecast error is just the forecasts. Let's say that we have time here, and we have time capital T here, and we have data from time 1 to capital T, and then we have some forecasts for time t plus 1, some forecasts for t plus 2, and t plus 3. Okay, and we have these forecasts, right? And we have the actual values here, and then we can just take the difference between these values. We can take the forecast error. The forecast error would be the actual value minus the forecast, and this we can square. Okay, so we can take the squared forecast errors for each of these, in our example, 3 points, and we can try to find the expected value of that. And just remember that the expectation operator is just giving you the average. Okay, so whenever you see this this expectation operator, think average. Okay, so what is the average squared forecast error? So your first step is to actually calculate the forecast error. So you calculate this for all the forecasts that you have done. Maybe you have made a 1 period ahead forecast, and then the next period you made another 1 period forecast, and the next period you made another 1 period forecast, which and you can use the data, the actual data, to improve your model up until that point where you want to create a 1 period ahead forecast. So at time t plus 3, you have observed your estimate and the actual values, and you can just take the, let's see, we can do that here. We can take estimate for time t plus 1, time t plus 2, for time t plus 3. Let's see, we can do this. And we can take the actual value, and we can subtract these and get the forecast error, right? And in this next column, we can take the squared forecast error, like this, and then we can just take the average of these squared forecast errors. Okay, so if our estimate in the first period was 1 and the actual price was 2, then our forecast error is 1, right? And the squared forecast error is just 1 squared, which is 1. And if our estimate in the second period was 3, and it turned out to be 3, then the forecast error would be 0, and we would have the squared forecast error would be 0 because that's 0 squared. And if our estimate in the last period was 5 and the actual turned out to be 4, then we have a forecast error of -1, and -1 squared is just 1. And then we have all the forecast errors. Then we could sum these 3 forecast errors, which is 3 of them, which are there are 3 forecast errors, but the sum of them are 2. So this is the mean squared forecast error. And one thing which is important to know is that the mean squared forecast error is often, or actually most often, just written mean squared error. And this mean squared error, it kind of resembles the variance, right? So whenever you see mean squared error, just think variance. And to get the sample equivalent here, you could subtract 1 in the denominator, because you get the then you get the unbiased sample mean squared forecast error. Okay, so but important, if you have a lot of data, then the mean squared forecast error and the sample mean squared forecast error, they are very, very similar. So to get an error measure which is a bit more tangible, right? We can take the square root of the mean squared forecast error, and what we get is kind of the standard deviation of our forecast error. And this root mean squared forecast error is more often just written root mean squared error. So if you want to Google MSFE, or you can just as well Google the root mean squared error. And this kind of gives you the standard deviation of the forecast error, and you know how to calculate with the standard deviation of stuff. How can we decompose this mean squared forecast error? So the mean squared forecast error is given to us by this expression, and let's assume that in our model the residual term is homoscedastic. Homoscedasticity means that the residual term has a constant variance. Okay, so what is the forecast error? It's the actual let's see, value minus the forecast. Okay, so the forecast is given to us by, or is created by, using the estimated regression model. And we have this negative sign here, so we have negative beta naught hat and negative beta 1 hat times the actual value at time t, because it's the actual value at time t or time capital T, that we use to make the forecast. But more intriguing is this term, which is the actual value at time capital T plus 1. And let's just look at this. This is the population regression, right? With information from time capital T, which means that we kind of have the actual residual and the actual population regression, which means that we can add these and get the actual value at time t plus 1. So the actual value at time t plus 1 depends on the actual value at time t and the residual at time t plus 1. Because remember that the regression equation, the population regression equation, is given by the following: yt plus ut plus 1, right? So this is just what we have down here, okay? So let's see. So if we just combine the y of capital T terms, we get that here, and we can combine the intercepts, which is here, and we have the population residual. So the mean squared forecast error, if we take the variance of this, we see that we have this, which is the population residual regression error, and we have this term, which is the estimation error. Okay, so this is the estimation error of the intercept. This is the estimation error of the slope, and this is times the actual value of y. So we can decompose the mean squared forecast error in one estimation error and the residual variance. So what we mentioned is that the expression in this equation can be used to show that the mean squared forecast error has two sources of error, and one is the error because we do not have information into the future, and we do not have information of variables which affect the level of y apart from our lagged value. And the second error is in estimating the regression coefficients. The first term in this equation is quite easy to calculate because it's estimated by the square of the standard error of the regression. So this is just the variance of regression residuals. So, or estimated by, I should say, but let's estimate it by the variance of regression residuals. And so this first part is actually quite easy to calculate. And in Stata, this variance of regression residuals is called root MSE. So you get it from the standard regression output. And the second term, the error in estimating the regression coefficients, is more tricky to calculate. And next week we are going to look at the variance of pseudo auto-sample forecasts and how we can use them to calculate the estimation error. If our sample size is large and we have specified our model correctly, which means that we have enough lags or the correct number of lags in our model, then we get consistent estimates of the regression coefficients, which means that the, let's see here, the intercept or the intercept here, the sample intercept, our estimate, is in probability going towards the true value of the intercept. So the population intercept. And the same goes for the slope, that if we get more data, then in probability we get closer and closer to the true population estimate, okay, or true population coefficient, because the population coefficients are not estimates, they are often unobserved true values. So if we have a large sample size, then the first source of error, which is the standard error of the residuals, is quite a bit larger than the second source of the mean squared forecast error. And what we can say is that the estimation, the second source, is the estimation error, and this kind of diminishes if we have a lot of data. So what we can say is that the root mean squared forecast error, which is just the square root of the mean squared forecast error. So remember that the mean squared forecast error is just the variance of the residuals, and this mean squared forecast error is just equal to the population residual standard deviation. And what we can do is that we can estimate this by the standard error of the regression. So we can use the standard error of the regression to kind of give an estimate of the mean squared forecast error and the root mean squared forecast error.